Hello again and welcome. A few months ago I posted a comment up on EEV blog where I was providing an opportunity for viewers to select some low-cost meters to test again. My only criteria was that the meters had to cost less than $60 with shipping. They had to be available on eBay or Amazon. Basically I was just looking for meters that I could easily obtain. I required that they all be auto-ranging, and the only reason for that is because of the length of the time that it takes to check a manual range meter. I wanted to look at meters that we've not previously tested, and I wanted them all to be 2,000 counts or greater. So this is the first meter that we're going to be looking at. This is made by UNI-T. Yeah, I swore I'd never look at another UNI-T product, but here we are. This is the UT125C. A member by the name of Grand Chuck had selected this meter. Just looking at the box, you see this here where it says overload protection. Of course, that's the whole point of these tests, is to figure out just how well they are protected. They call it a pocket multimeter. On the back of the box we can see some of the basic specs. You can see it can read up to a 40 meg resistance. You can see they have a drop test rating of 1 meter. Let's go ahead and open this up. We'll have a look at it. Again, I'm not going to be testing these meters in any specific order. Comes with a set of batteries. Looks like a little printed manual or a pamphlet. So again, I can't stress this enough, but the tests that I perform here really have nothing to do with the safety standards. And the reason I bring that up is we can see right here they have safety instructions, safety standards, conforms to 61010. And I've continued to stress that this testing is really about how electrically robust these meters are. So what I'm normally looking for in the standards that they pass are 61326, which is a EMC standard, not the 61010. What I've found is that meters that actually pass that 61326 standard usually do pretty well in these tests. A couple of things that I don't like about this meter right out of the gate. First of all, it has the leads attached. So I guess with it being a pocket meter, that's a benefit. But now you can see right here, this meter has a current mode, so it can measure milliamps and microamps. So I'm a little concerned that if this uses an internal fuse, what can end up happening is we pop that fuse when we're doing our other testing, and that could render the meter unfunctional. So the first thing I'd like to do with this is just install a couple of batteries, and let's see if it's even functional. Notice that they clearly mark the direction of the batteries. Let's see if it'll power up. No problem. Tell you what, let's get our little test box out here. That'll just help hold the meter while we do a simple functional test. Let's just start with voltage. I assume this will auto range from millivolts to volts, so this will be 5 volts. Looks fine, 4.99. This should be roughly 70 volts AC. And you can see it reads 65.8. This should be about 115 millivolts. You can see it reads about 128. Let's just try it at frequency. So this is going to be 60 hertz. You can see it's 59.9. Let's try it with AC plus DC at 60 hertz. Oh, you can see it can't read that, so this particular meter requires the zero cross in order to measure the frequency. Alright, so let's just try resistance. This will be with a short. This is going to be 50 ohms. Well, it's slow, so 50.2. This will be 100 ohms. It's reading 100 point. Jeez, again, very slow to settle. 100.0. Again, this is a 0.01% part. This will be a 1K ohm resistor. A little faster settling. Here it is at 10K. Here we are at 100K. Here's a 1 meg. This is a 10 meg. Again, this is a 0.1% part. And this will be a 40 meg, which is the upper limit of what they claim the meter can read. And it's reading 39.87. Let's try capacitance. So again, there's no way to zero this out, but this would be 160 picofarads that it's reading. Let's just try adding 150. See if it reads about 300. You can see it reads about 430. This will be a 1 nanofarad. See, it's reading a little high at 1.43. This is a 0.1 microfarad. Yeah, 100.9 nanofarad, that's good enough. This is a 1 microfarad. Pretty close, 0.997. Here's a 10 mic. .23 it looks like. Again, look how long it's taking to auto range. We'll just let this settle down. And here we are again with our 10 mic. So it takes a few seconds. This is with a 100 mic. Huh. Overranging, is that right? It's a little odd because the box claims this can read 100 microfarad capacitor. I would think that there'd be some tolerance on that. And this capacitor is fairly close to 100 microfarads. Yeah, it overranges. Alright, let's try the diode check. So here is 1 silicon diode. Here's 2 in series. Oh, it can't read 2 silicon diodes in series. Let's try it with our white LED, and of course the voltage is too low to light our LED. Alright, let's look at the continuity test. You can see it's a non-latching type. Probably quite fast. I'm not going to measure that. Let's just look at the current real quick. So this will be in the microamp mode. It should be 100 microamps. You can see it's fairly close at 99.6. This will be 10 microamps. And you can see it's reading 9.9. Right, before we get into this too far, let's go ahead and take this meter apart. Again, I'm a little concerned about that fuse input being shared. I just want to make sure that this uses some kind of a resettable fuse and not a mechanical fuse. So there's a couple of things I'm noticing right off the bat. First of all, we have a mechanical fuse in here. The next thing I'm noticing though is, look at the size of this PTC. See how much larger the body is on this one than this one here? Typically what I've seen with these cheap meters, they'll use these 5mm PTCs and then they have nothing else to limit the current through them. So it's up to the PTC to handle all that voltage. Once we start transient testing them, typically what will happen is they break down, it blows this casing off of here, it arcs over, and now there's nothing to limit the current. All that current then goes through whatever secondary clamp they have. Of course, then that blows those parts up. Transient continues down to whatever their control IC is, and then will blow the cover off of the IC. So it's nice here to see this larger PTC. I don't know why one is large and one is smaller. You'd really have to trace this circuit out. It's probably not worth the time to do that. The only thing that I notice right here, you can see they have some kind of a makeshift spark gap in the board. I don't know what all that's about. This is obviously the ground here. I kind of wonder what that's routing to. So you can see here's our red input wire attaching right here. This goes up to the one side of the fuse. And then here's the other side of the fuse, which is going straight over to the spark gap. Yeah, I'm not sure what they're trying to achieve there. It's obviously some kind of protection. Normally you're not going to use a spark gap on the back side of the fuse. So I can tell you right now, if we have this fuse installed, probably what's going to happen is when I transient test this device, that transient of course feeds through the fuse, then straight across the spark gap, and of course the current is going to be high enough it's probably going to take out our fuse. So I think what we should do is probably test this without the fuse installed. Again, we're primarily concerned about the voltage inputs, and it doesn't appear that running this without the fuse is going to affect those measurements. So let's just go ahead and we can check that real quick. We'll just install that single screw for now, and let's see if this works. So here we are. You can see it's reading a short just fine. Again, this is our 0.1 microfarad. And you can see again it's reading about 100.9. And again, this should be roughly 5 volts DC. And you can see it's reading 4.99. So I think it's okay to run this without the fuse. So I'll go ahead and put the other screws back in and we can button this back up. So this is our homemade ESD gun. We're just going to be using this as a DC power supply. Again, this meter here is in kilovolts. Let's go ahead and start turning up the voltage. So this is about 330 volts. Here's about 600, here's 700. And right here you can see at 1,000 volts. It overranges, but no problems reading the high voltage. So off to the left you can see I have our high voltage pulser out. Again, this is attached directly to our UNI-T meter. Currently I'm putting out I think 300 volts AC. Let's just do AC mode. We'll check real quick. Yep, you can see roughly 300 volts. The DC voltage is essentially nothing right now. So we'll go to AC volts. And again, this is with a positive DC bias. And here it is with a negative DC bias. Let's go to the higher voltage range. See, we're putting out about 600 volts. And again, this will be with a negative bias. Let's just go to DC mode again. You can see we're putting out, and it's about 530 volts there, DC bias. So let's try adding a positive DC bias. And you can see it really has no effect on the meter at all. So that's good. So I think with this particular meter, we're not going to spend a whole lot of time running any other tests with this. Let's just get right to the transient testing. So unfortunately, again, we have to use the leads that are supplied with it. So we'll just be using these banana adapters. You can get these from a lot of different places. These are from Pomona. This is how we'll attach to the transient generator, like so. I have not turned this transient generator on since the last time we used it. Let's see if it turns on at all. Hey, it does. So the very first test we're going to do is apply a 240 volt full wave rectified signal into the meter directly. So let's go ahead and we'll turn it on, and you can see the meter is reading 115 volts. That's correct. And now what we'll do is cycle the switch through the different modes, which there's only 2. I'm sure that's heating the PTC. Oh, look at this. It's actually locked up the meter. Let me zoom in here a little closer for you. So you can see I've got the volts mode selected and the meter's displaying ohms. Let's try turning it off. Turn it back on and see if it resets. And you can see it's displaying 232 volts DC. Again, 115 volts AC. And again, I'm going to go to the resistance mode, and it's flipping out. It's probably heating up that PTC, I'm sure, right now. But notice when I change the selector back to the volts mode, it's not happy. It's staying in the resistance mode. Huh. Well, it's really wigging this thing out. Let's just see if it works at all still. Notice it's picking up that voltage from the transient generator. I don't know if the camera is picking that up or not. Give you a little bit of shade. See how the LED is flashing? All I'm going to do is turn off our AC line voltage. So it's sensitive enough that it's picking up these cables that are running underneath the test box. Again, this will be a 1 mega ohm resistor. Here's our 10 meg. Again, taking a little while to reset. Here's the 100K. So yeah, it doesn't look like we've damaged anything. This is our 50 ohm. That looks fine. You can go to continuity. Just as scratchy as before. And again, this capacitance, we'll just check it at 0.1 microfarad. And you can see it's reading spot on still. So the next test we're going to perform is the ESD test. And we're going to be using this gas grill igniter to do that. Again, I've characterized this gas grill igniter. If you're interested in seeing what the wave shape off this looks like, I suggest having a look at my review of the UT181A, where I go over what the waveform looks like and how it compares to the IEC standard. So what we're going to be doing is attaching this directly to our clip leads here, like so. And then we'll be doing a direct contact to the other lead. We'll be applying 5 transients to the 2 modes of the meter, and then to do the negative transient, I'll just reverse the 2 leads. And again, we'll just invert the 2 leads to do the negative transient. And we'll go back to the voltage mode. And that's it. So let's just see if it can read a short. There you have it. This is so rare to see a UNI-T meter survive that gas grill igniter. You kind of wonder, has UNI-T been paying attention to these tests? Maybe they've been embarrassed that so many meters pass, but basically all theirs fails. Let's just start again with a 50 ohm resistor. And you can see spot on 50 ohms. Here's our 100. Looks good. Here's our 1K. Looks good. Here's the 10K. Looks fine. 100K. Looks fine. Here's the meg. Looks fine. Here's the 10 meg. And that looks fine. Again, we'll do diode check. So here's a single silicon diode. That looks fine. Continuity mode. Of course, that's fine. And we'll do capacitance again. So here's our 0.1 microfarad. Looks good. And let's just try it with a larger one. So this is our 1 microfarad. It looks good. We'll go back to DC volts. Again, this should be 5 volts DC. Spot on. And let's try it at a higher voltage. So again, this should be about 60 volts or so, and you can see it's reading 57.5. That's good. And let's try AC volts. So again, this should be closer to 70, and you can see it's reading 65.7. And we can do frequency again. So again, this should be roughly 60 hertz. So no problem. Looks like the meter survived this test just fine. Very rare. So to continue our ESD testing, we'll be using our homemade transient generator. Again, the waveform off of this transient generator is very close to what the IEC standard calls for. Again, we'll be applying 5 transients, both positive and negative, to the 2 modes of the meter. Alright, so here we go. And again, we'll flip the 2 leads to do the opposite polarity. And that's it. Again, let's just go to resistance. And just the fact that the meter is reading an open right now pretty much guarantees that this did not damage the meter. Here you can see with the 2 leads shorted, looks like it's reading roughly 0 ohms. So let me go through. I'll functional test the meter off camera. Next we'll be performing our transient test, In order to use the leads that they've supplied with this meter, you'll notice that I don't have my oscilloscope probe out, so we won't be monitoring the transient voltage coming off of this. Now, really, that's not a big deal. Again, the only thing that I really use that for is it gives me some kind of a heads up if the meter's starting to break down. So we're going to be starting at 1000 volts peak. So this will be 1000 volts with a 100 microsecond full width half height, 2 ohm source impedance. And again, we'll be applying 5 transients to the 2 modes of the meter, and then we'll flip the polarity by swapping the 2 leads here, and then we'll functional test it. So let's go ahead and get started. You can see each time the transient generator strikes, we get our little non-contact voltage lamp comes on. And again, we'll just flip the polarity of the 2 leads and repeat our test. Okay, that's it. I'll go ahead and functional test the meter. Alright, so the UT125C survived that 1000 volt transient just fine. Transient generator is now set for 1,500 volts peak. Again, this will be a 100 microsecond full width half height with a 2 ohm source impedance. Again, this will be 5 transients, both positive and negative, with the meter set to both modes. And again, we'll flip the leads around to run the opposite polarity. And that's it. Alright, so the UT125C survived that test just fine. I've reprogrammed our generator for a 2000 volt peak transient. And here we go. And that's it. Alright, so the UT125C survived that 2000 volt transient just fine. I've got our generator set for 2,500 volts. Again, this is a 100 microsecond full width half height, a 2 ohm source impedance. And we'll be applying 5 transients, positive and negative, with the meter set to the 2 modes. Okay, that's it. So the UNI-T UT125C survived that test just fine. I've reprogrammed the generator for 3000 volts peak, 100 microsecond full width half height with a 2 ohm source. Alright, that was 3000 volts peak. Let's just do a real quick check here. Put the meter into resistance mode. Just the fact that it's reading an open and a short. Probably have not damaged the meter. I'll go ahead and check it off camera. But so far, I'm pretty impressed with how this meter's holding up. Alright, so the 125C survived that test just fine. I've reprogrammed our generator for 4000 volts peak. Again, this is a 100 microsecond full width half height, 2 ohm source. Okay, that was 4000 volts. Again, let's just change it to resistance mode. I've not heard any kind of a physical noise coming from the meter signaling that it's starting to break down. Alright, so the UNI-T survived that 4000 volt transient. I've reset our generator for 5000 volts peak. So again, this will be 5000 volts, 100 microsecond full width half height with a 2 ohm source. 5 transients each. Alright, that's it. I wish I wouldn't have shut the camera off. So all I did was just rotate the switch back to the resistance mode. And you can see right there, leads are open and she's measuring 5.5 ohms resistance. You can see diode check mode. It's reading a short. That's continuity mode. Let's try it with the voltage mode. And let's just apply our 5 volts DC. And you can see that is spot on. My guess is the only thing that's wrong with this is we probably took out a set of clamps. So yeah, it looks like it's failed at 5,000 volts. We'll go ahead and pull this thing back apart. And let's see what went wrong with it. You know, just doing a quick check, it's very possible it could be this Q3, Q4 right here. See that? That one is shorted. And if we look at the other leg, that's shorted as well. Tell you what, let's just take this circuit board right out of here. You guys wanted to see what this looked like anyway, I'm sure. I'm just very impressed that this meter took this kind of abuse. What's up, UNI-T? Have you been paying attention to these videos or something? I mean, I would have bet money that this meter would have been damaged during that ESD testing. Switch looks fairly typical for a UNI-T. Actually, I wish they had put contacts like this in that UT210E I've got. Notice they've greased the contacts here. You can see the sheen on there. Look at this area here where there's no grease. Now look around the rotary switch. Alright, let's just have a look real quick with that function switch removed. Are these still shorted? Sure enough they are. I'll bet you that these two transistors here are making up that high-speed clamp. These are marked Y1. I think that that's a common part for them. Normally I would have pulled these with the heat gun, but I really like using these paste micro tweezers that I bought. Those make it very quick to pull parts. So again, these parts are marked Y1. And sure enough, you can see out of circuit, that one is definitely shorted. And let's check the other one. Yep, sure enough. So both of those are shorted. My guess is the meter would probably functionally be fine right now. What I'm going to do is go ahead and replace those two transistors with another part. I probably won't use a Y1. I've actually got those upgrade transistors that I used for this Bryman when I upgraded it. Looks like we still have a few of these left. The pinout for these will be the same as what was in there. I'm sure this board is all lead free coming out of China. Still, we're going to go ahead and remove the old solder. This takes a second. Normally I'd do this with the microscope, but we're just going to free hand this. Again, we'll be using leaded solder. Let's check it real quick. Hey, it's actually got a transistor in there now. Look at that. Okay. Let's go ahead and we'll put this thing back together. So if you're going to take one of these apart, my advice would be to leave these two top screws in place. This is the light pipe for the non-contact voltage detector. This just fits into the groove like so. I think we're ready to snap this back in place. And before we do anything, let's just go ahead and turn this thing on. Is it reading open now? Sure enough. Let's just try reading a resistor real quick. This will be 100 ohms. And you can see 103.2, 102, 101, 100.9. Yeah, okay. Let's go ahead and we'll finish buttoning this up. You can see my soldering there isn't the greatest. I think we'll go ahead and reinstall the fuse. And you can see I've just taped the two dead transistors to the back cover. Just as a reminder, if I ever wanted to put this thing back to stock. Alright, let's just go through a real quick functional test. So first of all, let's check the backlight. Let's see, that still works. It's not very bright, but that's okay. Again, this will be 5 volts DC. And just like before, 4.99. And again, this should be roughly 60 volts. And it reads 57.6. Again, let's try frequency. Should be 60 hertz. Looks good. Let's just do our 40 mega ohm. And there you go. So 39.8. This will be our 10 mega ohm. Again, this is a 0.1% part. You can see it's 10.01. This is a 1 meg 1% part. This is a 100K 0.1% part. This is a 10K 1% part. This is a 1K 0.1% part. This is a 100 ohm 0.01% and a 50 ohm 0.01%. Bounces around a little bit. So again, this is diode check mode. Here's with an open. Here's with a short. And here's a single silicon diode. So continuity mode. Scratchy just like before. And let's try capacitance. So again, this will be a 0.1 microfarad. And you can see it's reading 101 nanofarads. And here's our 1 microfarad. It's reading 0.997. And here's our 10 mic. It's reading 10.23. So no worse for the wear, I guess. Well, I think that's going to be it for this video. So again, I'm pretty impressed with the UT125C. Meter held up quite well. So maybe UNI-T has had a change of heart and is actually going to make some robust meters here in the future. I'll tell you, I wish their UT181A was as robust as this was. Of course, one of the big advantages to this meter is we were able to repair it. Normally what happens with these cheap meters, they go into the scrap bin. Of course, this is the last meter I looked at. This is the UNI-T UT125A. This meter was also damaged during this transient testing, and we can't repair it. It uses a lot of custom parts and they're not available. So this meter is basically scrap. This meter I would expect to be far more robust than what this little UNI-T is. And if anything went wrong, I would expect we'd be able to repair it. So you don't always get what you pay for with these meters. Well, that's going to be all for now. I hope you enjoyed it. Hopefully you had an eye-opener experience like I did. Until the next video, we'll see you then. Later.